Hi, I'm EJ, which is short for Evert-Jan Bakker. I teach statistics at Wageningen University since 1998. I will give the first 4 lectures in the course Advanced Statistics. Welcome to the course. I will immediately dive into the contents itself, and that is statistical inference, and in particular confidence intervals and t-tests. In statistics, the main aim is to do inference. That is, to draw conclusions about a population or about a general phenomenon based on a limited number of observations. These observations are the sample data. The most common forms of inference are hypothesis testing and making confidence intervals. Today, we will review the so-called t-procedures, that is, tests and confidence intervals in which a t-distribution is used. We will see how to apply these for the first 3 situations discussed in this course. You can find the list of all situations of the course on pages 6-7 of the study guide. The first situation is that of one sample, where we are interested in the population mean of one variable. For example, we're interested in the mean body weight of all 6-year-old children in the Netherlands. The second situation is that of paired data. For example, we measure the birth weight of twins. one measurement for the firstborn, one for the secondborn. Or we make measurements on a plant, animal, or human being before treatment and after treatment. In the third situation, we have 2 populations that we compare. For example, we're interested in the difference in exam scores between male and female students. This is an example of observational research. In experimental research, we start, for example, with 20 pots with a peanut plant, and 10 of these, randomly chosen, will receive one treatment and 10 receive another treatment. In this way, we also obtain data for 2 groups. In the first lecture, we will use an example for each of these 3 situations to discuss the ins and outs of confidence intervals and t-tests. Some issues will be explained and some will be taken for granted, as they have been discussed in previous courses that you followed before. A few words on the process of inference for a simple case. We have a population, and in that population we're interested in a certain variable, body height, growth, yield, and in particular you want to know what the mean of that variable is, the mu of y. Well, to get an answer, we obtain information. How do we do that? We take a random sample. And from that sample, we measure the variable, and in that way we get sample data. The sample data contain signal that is really representative of the population, but it also contains some noise, which would vary from sample to sample. If you would take many samples, each time the noise would be different, but the signal would be, let's say, the same. Well, using the sample data, we would then draw conclusions. Important is that we realize that when we draw the conclusions, that they are partly based on noise. And so they introduce a certain level of uncertainty in our conclusions. That is why we do tests with a so-called significance level of alpha, usually 5%, and we have confidence intervals of 95%, for example. This is all necessary and required because of the uncertainty that random sampling takes with it. The rest of this lecture consists of 2 parts. Part 1 is about confidence intervals. Part 2 is about t-tests. The confidence intervals part is built up as follows. Each time I will introduce an example of a situation, the one sample situation, the paired data situation, and the two independent samples situation. And I will end with showing how to derive, how to calculate the limits for a confidence interval for that example. For the one sample case and the paired data case, I also include some general information which is of general importance, namely confidence intervals as a topic and the 4 elements of T procedures. As we will see, they play a very important role in easily doing these T procedures. First of all, the learning goals for confidence intervals. There are 3. You have to be able to explain what a confidence interval means. Confidence interval for a parameter, so-called parameter of interest, that is a population characteristic. Secondly, you have to specify the general pattern of a confidence interval. And thirdly, you have to be able to apply this pattern to a specific problem. And specific means that you know which situation applies, and connected to that is what are the 4 elements for that case. The general pattern of a confidence interval uses the 4 elements of T procedures. I can already mention them: the parameter of interest, the estimator, the standard error, and degrees of freedom. And in each situation, the set of these 4 elements is different. So these are the learning goals. First example. Example for the one sample situation, one population, and one variable for which I'm interested in the mean. Suppose I walk around the campus and I go for a coffee into Forum and I observe some very tall male students. Now I might wonder, what is the mean body height of male Wageningen students? And has it changed since 1980? And for that period I happen to know that it was 180 centimeters. So these 2 questions will be answered in this lecture. Question 1 by doing a confidence interval, and question 2 by doing a t-test. Well, how do I move on? First of all, I take a random sample of all male students, and in this case I will take 25, and I measure their body height. And the miracle, if you would like, of statistics or of inference, is that we are able to draw conclusions about a large population based on only these 25 observations. So from few to many, that is the miracle of inference. Of course, the conclusions that we draw are not exact, and they will come with a level of uncertainty. Well, some sampling terminology. We're interested in the mean of one trait, in this case body height, in one population. So population is really a key word. The population here is that of all male Wageningen students. The students are also the sampling units. In this case, we do observational research. We draw a random sample of an existing physical population which we observe. The response variable is body height. It's measured per student, so the student is also the observed unit or the measurement unit. The scientist, or in this case we draw conclusions about the population mean of body height based on one random sample. So we also refer to this situation as the one sample situation. And the other way to refer to it is one population, one mean. The population is a physical population and the type of research is observational. Another important term is the parameter of interest. The parameter of interest is what you would like to know, what you want to draw a conclusion about. And in this case, it is the mean body height of all male Wageningen students. Usually we denote the parameter of interest by a Greek letter. In this case, we use the letter mu for mean, or the mu of y, the mean of y, and y is then the body height. To answer question 1, we will show how to make a two-sided confidence interval for mu. To answer question 2, is mu different from 180? We will do a one-sample t-test. The following information is used to make a confidence interval. That is the summary statistics for this data set. Well, we had a sample size of 25. We have a sample mean of 184. And we have a standard deviation of 9. And the standard deviation tells us how variable the observations are in the sample, and but likely also in the population. Okay, well, first of all, let's look again what confidence intervals are, a few characteristics of these. It's a range of likely values for a parameter. And again, a parameter is something that describes a characteristic in the population. In our case, the mean body height of all male Wageningen students. So the confidence interval is a range of values for the parameter that we have confidence in. So we found as an estimate 184, so we think, well, it could be maybe 184, but maybe also 182 or maybe 185. So these would then be part of the confidence interval. The confidence interval level is indicated by 1 minus alpha, is usually 95%. And it gives, as it says, the level of confidence that we have. The width of a confidence interval reflects the precision of the estimate. A precise estimate gives a very narrow interval. An imprecise estimate gives a very wide interval. The bounds or the limits of the interval are random. They're calculated from the data, and the data depend on the units that we have drawn in the sample. The 95 or the 1 minus alpha in general, what does that mean? Well, it says something about the method. The interval is constructed in such a way that the probability that the interval will contain the true parameter value is 95%. So you could think of doing the whole experiment and then the calculations many times, let's say 1 million times. And from all these million times, you get 1 million intervals. And out of all these intervals, 95% will contain the true parameter value and only 5% will not. And notice that in practice, we only have one sample. So it's really about the method and not about the outcome of the confidence interval. Confidence interval is typically of the following form. It is a guess, a best guess, known as estimate in statistics. Estimate plus or minus an error margin. Well, what is the general structure of a confidence interval? So this is the second learning goal. Well, the limits of a two-sided 1 minus alpha confidence interval for a certain parameter is given as follows. It's the estimate plus minus a t-value, a quantile from the t-distribution, which we can look up in Ott and Longenecker table 2, times the standard error. Yeah, so it's estimate plus minus t times standard error. The t is a constant, and it depends on the degrees of freedom and on the alpha. And for the one sample situation, yeah, we now get these 4 red parts that we have indicated. The parameter is the population mean, the mu in this case. The estimate is the sample mean, y bar. Yeah, so the sample mean is used to estimate the population mean. The standard error of y bar is the standard deviation divided by square root n. So it has also been discussed in the previous course, so we're not really going into that. You can find it in Ott and Longenecker. And the degrees of freedom for the t distribution that we need is n-1. Well, so for the population mean mu y, a 1 minus alpha confidence interval then is, yeah, for the one sample situation. Well, the estimate is y bar. Then we have plus minus. The t and the alpha divided by 2, they stay the same, but the df is now replaced by n-1. And the standard error is given by standard deviation of y divided by square root n. Yeah, so this is the general structure of a confidence interval applied to the one sample situation. Now we will go to our own case, our own example. Yeah, the general formula is y bar plus minus t times standard error. And in this case, we have sample data, n is 25, y bar is 184, and the standard deviation of y is 9. The T24 value of 2.5%, yeah, can be found in Ott and Longenecker, but can also be found using PQRS, a very handy program. Yeah, we look in PQRS and we look here at the t distribution with 24 degrees of freedom, and we look at the quantile with 2.5% at the right-hand side. The right-hand side tail probability is 2.5%. So, and then for that particular value, we get a t of 2.064. So the T24 of 2.5% is 2.064. You could also find that in Ott and Longenecker. So the lower bound of the confidence interval is y bar 184 minus the t value 2.064 times standard deviation 9 divided by square root 25. And that happens to be 180.28. The upper bound is calculated similarly, 184 plus 2.064 times 9 over square root 25, and that is 187.72. Yeah, the error margin is 3.7. Yeah, the two-sided confidence interval for the mean body height of all male Wageningen students is 180.3 to 187.7. So now we come to the second example, example B, and it is an example of paired data. It's about blood pressure change. A physician records the blood pressure before and after 2 weeks of medication use for 16 patients. And the difference in blood pressure is called D. She regards the 16 patients as a random sample. First question that we could ask, what is, in general or in the population, the change in mean blood pressure after medication use? So we will look at mu x minus mu y, or what is the mean change in blood pressure, mu d, after medication use. Yeah, so the first expression is the change in mean, mu x minus mu y, and the others is the mean change, mu of d. And the two are the same. Question 2 could be, does mean blood pressure in the population go down after medication use? And in symbols that would be mu x minus mu y larger than 0, or mu d larger than 0. A note: for paired data, the observations x and y within the pair are not independent. They belong to the same unit and will be correlated. Yeah, this problem, as we will see, is solved by using the values of the differences. A second note: if the sample would be random, in this case it was not, the patients are independent units. Yeah, and that's why it is important that the physician regards the observations as independent. Yeah, so if you would have 5 family members at a row or so, yeah, this the independence would no longer hold. Well, some design notions for this case, and what we will see is that paired data design is the same as a one sample situation for the differences. Well, first of all, the patients were not randomly selected. What would you do in practice? You would check, is the proportion male and female, is that similar as in the general population? Is the age distribution like that in the normal population? Is the weight similar, etc.? Yeah, and that is to see if the sample may well represent the population. May not be easy in this case because the population is already a special group, namely patients with high blood pressure. Yeah, we measure blood pressure before and after medication use. The population could be all patients in this practice or in the Netherlands that have high blood pressure, if they would use this medication. Yeah, but you see it's not very well, very precisely defined. The patients are the sampling units. The response is the blood pressure measured twice per patient. And the patient moment combinations are the observed units or the measurement units. But there is a second way in which we could look at this case, namely, the response is the blood pressure change, D, and the patients are the sampling units and the observed units, the measurement units. And this shows that the paired XY observations case is equivalent to the one random sample case with D as the variable of interest. Yeah, so the paired data observations case is the same as the one sample situation applied to the differences. In this case, the parameter of interest is the mean in blood pressure change or blood pressure difference before and after in the population. And we will note this parameter of interest by mu d. And then you see that it's very close to what we saw in the one sample case. There we had the mu of y, and now the d replaces the y. To answer the first question, we will show how to make a two-sided confidence interval for mu d. And to answer the second question, is mu d positive, we will do a one sample t-test. We need the following information from the blood pressure data: summary statistics. We see as a sample size n is 16, the sample mean d bar is 6, and the sample standard deviation is the sample standard deviation of d is 12. What we see here is that we do not have data on x and y. And the interesting thing is, for this particular case, that we don't need the values for x and y. Of course, we would also have them, but they're not needed in what follows, in making the confidence interval or doing the t-test. An extra topic, let's say, a core topic also in today's lecture, is the 4 elements in t-procedures. Yeah, we need them in confidence interval calculations and in the t-test. In any procedure, 4 elements are central, and we have already named them. The first is the parameter of interest. It's a characteristic of the population, and it's this thing that we want to draw a conclusion about. Second is the estimator, which tells us how we estimate the parameter from the data. The estimator, you could say, is a method or a formula. In the first example that we had, we estimated the population mean body height by the sample mean body height. So y bar, the sample mean, was the estimator for mu. Well, the estimate is the outcome of the estimator in this particular data set, and that is a number. Yeah, so method and formula are contrasted to just simply a number. C is the standard error of the estimator, or the standard error of the estimate as calculated from the data. It's a measure of how certain we can be about the estimate. And this also comes in a formula and in a number. Finally, we have the degrees of freedom for the t-distribution. Yeah, in the first case, we saw that n-1 was these degrees of freedom. Well, a short overview for the first 2 situations shows great similarity between the two. The one sample case and the paired observations case, we see the parameter, estimator, standard error, and df, degrees of freedom. For situation 1, we indicate the parameter usually by mu, the estimator by y bar, if the variable is y, the standard error, the standard deviation in the sample divided by the square root of n, and the degrees of freedom n-1. And for situation 2, it's exactly the same, except that we now apply this to the differences between the 2 observations, x and y. So parameter mu d, estimator d bar, standard error sd over square root n, and degrees of freedom n-1. Well, the confidence interval for mu d now. The parameter of interest is the difference in mean blood pressure before and after. As mentioned before, we will use the confidence interval, and we will do this on the whiteboard using the fact that T15 0.025 is 2.131. The summary statistics are repeated again. N is 16, D bar is 6, and SD is 12. I have done some preliminary writing on the whiteboard. First of all, the summary statistics, N is 16, D bar is 6, and the standard deviation of D is 12. And then I've given the general formula for a confidence interval, 1 minus alpha confidence interval for a parameter is estimate plus minus the t-value times standard error. For paired data, the parameter is indicated by mu of d, the estimate is given by d bar, the degrees of freedom in the t-distribution is n-1, and the standard error is sd over square root n. So now we can use the summary statistics to calculate the confidence interval limits. So we get 6 plus minus a t with 15 degrees of freedom And since we wanted a 95% confidence interval, alpha divided by 2 is 0.025. And then times SD12 over square root of 16. I already mentioned in the slides that the T15 value is 2.131, so I get 6 plus minus 2.131 times 3. 12 divided by 4 is 3. So a 0.95 confidence interval for mean decrease in blood pressure is 6 minus, and here this is 6.4, so we get minus 0.4 up to 6 plus 6.4 is 12.4. 6.4, yeah, I could write that here, 6 plus minus 6.4. So the decrease could actually be an increase. Yeah, it could be as small as minus 0.4, so there could actually be a slight increase, but more likely there is an increase, and it can be as large as 12.6. So, back on my chair again. Once more the answer, 95% confidence interval for mu d minus 0.4 to 12.4. So we now come to the third example, example C, about tapeworms in sheep. And it's a case for 2 independent samples, or more precisely for the case of 2 treatments, where the treatments are randomly assigned to the experimental units. Well, what is it about? Researchers investigate the effectiveness of a new drug D for tapeworms in the stomach of sheep. They do an experiment. 24 sheep are used infected with worms, and they are randomly divided into 2 groups. Sheep in group 1 received the new drug, and sheep in group 2 received no treatment. The sheep are individually treated and kept, and not in groups. After 6 months, the lambs are slaughtered, and then the number of worms, indicated by Y, in the stomach of the sheep are counted. The setup. Yeah, we would like to compare, in this case, 2 populations. But they are not physical populations, but rather hypothetical populations. A is the population of sheep receiving the new drug, and B, the population of sheep receiving no treatment. In our study, we have, as it were, 1 random sample from population A and 1 from B. So this situation with 2 treatments, randomly assigned, is equivalent to the situation of the case where we have 2 physical populations, each of which gives us 1 sample. So the case of 2 independent samples. Yeah, and the 2 cases, observational research and experimental research, are analyzed in the same way. We make inferences about the difference between the 2 population means based on the data from 2 random samples, 1 from each of the populations. The sheep undergo the randomization, so they are the experimental units, a very important term, just like sampling units, because the units that undergo randomization can be seen as independent units. The response variable is the number of tapeworms in a sheep. And the sheep, or their stomachs, are also the measurement units, the units on which we take the measurement. Statistical model, something I did not really discuss in case 1 and 2. So let me do that now, because it's very important that a statistical model specifies what we assume about the data. Each statistical analysis is based on some kind of statistical model. Yeah, for example, if we do a t-test or make a confidence interval with a t-value for the one sample situation, we assume, whether we know it or not, that the responses y1 up to yn are independent and all come from one normal distribution. Yeah, so that's what we assume. And if that's not the case, if we have two completely different groups or so in our data set, then this may influence the results very strongly. Or if we make many measurements that are not independent, for example, people from one family or so, or repeated measures on the same individual, then the conclusions that we draw are also no longer correct because the model that we used was not correct. That is, the assumptions. Likewise, if we do a t-test or make a confidence interval with a t-value for paired data, we implicitly assume that the differences d1 up to dn are independent and all come from one normal distribution. In short, for these situations, we assume independence and normality. Now, example C, the sheep example. We assume that the 24 responses from the 24 sheep are independent. Why can we do that? Well, the treatments were randomly assigned to the sheep, and the sheep were individually treated and kept. So if the 12 sheep that are treated are kept in one barn and 12 other sheep in another barn, then it would be a case of n is 1 instead of n is 12 per group. But here the independence seems reasonable. We have real replications. In each of the two populations, the variable is normally distributed. That is the second assumption. The means in these two normal distributions can be different, mu1 and mu2. That's what we want to investigate. And in first instance, we will assume that the standard deviations in both groups are the same. And we indicate that standard deviation by sigma. So we can either say the standard deviations are the same or the variances sigma square are the same. In short, we assume independence of observations, normality, and equal variances in the two groups. Later on we'll also look at the case where the variances sigma 1 squared and sigma 2 squared are not the same, or equivalently the standard deviations sigma 1 and sigma 2 are not the same. But for now we will assume this. Well, the questions. The first question, what is the difference in mean number of worms between drug and no treatment? And then in general, so in the population. In other words, what is mu1 minus mu2? The second question, a bit more specific. Is the mean number of worms lower when D is used? In other words, is mu1 smaller than mu2, or is mu1 minus mu2 smaller than 0? So the first question again will be, we will use a confidence interval for that, and the second question in the second part with a t-test. Well, the following data are given, the summary statistics for drug animals. The sample size is 12, n is 12, y1 bar is 26.5. The sample standard deviation in group 1 is 14.36. For the non-treated lambs, N2 is 12, y bar 2 is 39.67, so we see it's indeed a lot higher, and the standard deviation in the second group is 13.86. Yeah, so these are the sample data, the summary statistics. Well, when we want to make a confidence interval for a certain parameter, in this case mu1 minus mu2, we need to know what are the elements for that situation. Well, the 4 elements in their standard notation are given in the following table. For situation 3, the independent sample situation, the parameter is mu1 minus mu2. The estimator is the method by which we estimate mu1 minus mu2 is y bar 1 minus y bar 2. The standard error, and this is explained well in the book, and we will just mention it here briefly how to use it. The standard error is the standard deviation times the square root of n over n1 plus 1 over n2, and the standard deviation SP is the standard deviation that is estimated based on S1 and S2, as we will see. SP is the square root of SP squared, and SP squared is the pooled variance estimate. It's a weighted average of S1 squared and S2 squared, and the weights are the degrees of freedom in each of the samples. So it's n1 minus 1 times S1 squared plus n2 minus 1 times S2 squared divided by n1 plus n2 minus 2. And the degrees of freedom that applies to the t-distribution is n1 plus n2 minus 2. Yeah, for the later case that we will discuss when the standard deviations are not the same, parameter and estimator are the same, the standard error has a somewhat different formula. It's also based on S1 squared, S2 squared, and N1 and N2. And in fact, the two standard deviation formulas give the same result if N1 and N2 are the same. So if we have a balanced data set. In that case, the standard errors for the situation 3 and 3b are the same. The degrees of freedom is not an exactly given number because the t-test and also the t-value for the confidence interval is not exactly known, but it's an approximation. And the degrees of freedom has the approximate degrees of freedom has a kind of complex formula which is given in the book, but we will not really look into that. Well, in our case, the variance formula SP squared is then 12, which is n1 minus 1, times 14.36 squared. 14.36 was the first standard deviation, and then plus 11 times 13.86 squared. 13.86 is the standard deviation in the second group, and we divide the whole thing by 24 minus 2. It gives 199.1, and so the SP, the pooled standard deviation, is 14.11. Yeah, so from this we see we had 14.36 and 13.86, so the 14.11 has to always be between these two values. If you come up, if you had found 15 or so or 12, then you know in advance that the answer cannot be correct, because it must be between, it's a kind of average of the two, so it must be in between. The confidence interval then, for the sheep example, the general principle, estimate plus minus a t-value times standard error. The estimate is based on the estimator, and the estimator is y bar 1 minus y bar 2, and the estimate, which is the outcome, happens to be minus 13.03. Yeah, if we subtract the two means, we get a negative number indicating that the non-treated lambs have more worms. The t-value then, df is n1 plus n2 minus 2 is 22. Alpha is 5%. So we need to look up the T22 quantile from the T22 distribution. And if we use PQRS, we can see that the T distribution, 22 degrees of freedom, 0.025, then we get 2.074, which is given here. The standard error was SP times square root 1 over 12 plus 1 over 12. SP is 14.11. And if we do the calculations on our calculator, we get 5.76. So the 95% confidence interval is minus 13.03 plus minus 2.074 times 5.76 gives as limits minus 25 to minus 1.1. Yeah, so we see that we're quite confident that the difference must be negative. In other words, the treated lamps have fewer worms. Yeah, so a question that we now also can answer after my last remark. If we test that the two means are the same, mu1 minus mu2 is 0 versus mu1 minus mu2 is not 0, would the null hypothesis be rejected? Answer: yes, it would be rejected because the value 0 is not in the confidence interval. Yeah, so that is one way of doing a test sometimes. Okay, this concludes our part 1 of lecture 1. We discussed the first 3 situations out of 15 in this course, so see page 6-7 if you did not do that yet. We discussed what confidence intervals are. Well, it was a brief review. We discussed the 4 elements of T procedures: the parameter, estimator, standard error, and DF. And we also saw what these are for the 3 situations that we looked at: 1 sample, paired observations, and 2 independent samples. Finally, we showed how to calculate confidence interval limits for a parameter for each of these 3 situations. And the general formula always is estimate plus minus T times standard error.